Hello, good morning to one and all. Today's lecture on the basic types of these signals. So these are the basic types of the signals we are going to be deal, and first one it is impulse signal, and second one it is a step signal, and ramp signal, and parabolic, and a rectangular, or you can call it as a gate function or a signum function, and exponential signal, sinusoidal signal, and sync functional, or you can call it as a sampling function. So if you look into the impulse signal, what is the definition of the impulse signal? The signal is represented by del of t. The signal is represented by the del of t, and its amplitude, its infinity at t is equals to 0 and 0 at t not equals to 0. This is about the continuous time signal. If you look into the discrete time signals, del of n it is, and where n equals to 0, the amplitude is 1, and n equals to n not equals to 0, the amplitude is 0. These are the two representation. One is in a continuous domain, del of t, and in a discrete domain it is a del of n. And how we are going to be in a graphical domain, let us see, it is a time t. It is a time t, and the signal is looks like this. At 0, the amplitude is infinity. At 0, the amplitude is infinity. You can represent it as a del of t. And when it comes to the discrete, you can call it as a n, and amplitude is 1 at 0, and the remaining is 0. You can represent it as a del of n. These are the two representation. In one is in a continuous domain, and the second one is in a discrete domain. Okay. Now next comes to the definition in full-fledged. If you said a signal is an impulse function, the impulse function must be obeys the two definitions. So two definition. First one is its amplitude must be infinity, and the second one is area under that same delta function, or you can call it as a del of t dt must be 1. So this is a second condition. So this is the second condition. The area under the impulse function must be 1. So this is the two conditions should satisfy any signal, then that signal can be represented as del of t, and it's named it as a impulse signal. So impulse signal has some properties. You can call some properties are there. The first one, as I mentioned, it is area under the impulse signal is infinity to infinity. Del of t dt is equals to 1, and this is a first one. And if you see the scaling property for this one, scaling property, if you take del of at, then the resultant is 1 upon magnitude of a mod a into del of t. So this is one of the property. And the next one, it is even property. That means del of t is a even signal. You can call it as a del of t is equals to del of minus t. And one more thing, it is a multiplication property. For suppose some x of t is there, this is some another signal, and I am multiplying with the del of t with some shift, del of t minus t naught, del of t minus t naught, then it could be x of t naught, whatever the shift is there, this shift is going to be replaced by t, x of t naught into del of t minus t naught. This is another property, and that is a multiplication. And one more, it is integral property. Integral property, that is, let us take integral t1 to t2. There are two time variables, that is a two time slots. It is from t1 to t2. In between, if x of t is multiplied by del of t minus t naught dt, its result is depends on if this t naught is in between t1 to t2. If t naught is in between t1 to t2, then its corresponding result is x of whatever the shift is there, that is value t naught. This shift will move to the t naught directly. We are taking at a t naught value. When this T naught, whatever the T naught is there, if this T naught is in between the T1 to T2. So if it is not, else in other case the value is 0. These are the four main properties. First one scaling, second one it is even function, third one it is multiplication property, fourth one it is a integral property. So this is about the impulse function. So impulse function we are representing like this. Amplitude is infinity, del of t 0, and representation in mathematical functional domain it is del of t is equals to infinity where t equals to 0, 0 where t not equals to 0. This is about the continuous time signal, right? Next one, step signal. Step signal you can call it as a u of t. Step signal is a u of t and its mathematical representation is u of t where t value, if t greater than or equals to 0, amplitude is 1 and t less than 0, amplitude is 0. And its mathematical, its a graphical representation is like this. This is t, this is a t and amplitude is, you can call it as a 1 at 0 and the name it as a t. And the same signal you can represent in discrete domain also, that is u of n. So how you are going to be represented? That is u of n is equals to 1 for n greater than or equals to 0, 0 for n less than 0. So how you are going to be represented in a graphical domain? So at 0 amplitude is 1, above 0 at 1 amplitude is 1. That means the remaining all values like up to infinity time 0, 1, 2, 3, 4. So this is the u of n. What about the at minus 1 amplitude is 0, minus 2 amplitude is 0. This is the graphical representation of the step signal in discrete domain u of n, that is a discrete domain, and u of t is a continuous domain. Okay, next, so here u of t is already there. Now what I am trying to do, I am replacing t with a minus t, u of minus t. So now if it is a u of t, then how u of minus t look like? So that simply you can call it as a flipped signal or you can call it as a time reversal signal. Time reversal signal. If u of t is like this, I mean from 0 to infinity, then u of minus t is from 0 to minus infinity. 0 to minus infinity. So how you are defining the u of minus t? U of minus t is equals to 1 where t less than 0, 0 where t greater than or equals to 0. So same. If you look at this one and this one, if you see the time values, at t greater than or equals to 0, 1 and t less than 0, it is a 0. Where comes to the u of minus t, this is a u of minus t, and t greater than 0, t less than 0, you will have the 1 and t greater than or equals to 0, it is a 0. Right? Similarly, you will have the same u of minus n signal, you can call it as a 1 where n less than 0, it is 0 where n greater than or equals to 0. That means the signal is look like this 0 n u of minus n now 1 1 1 1. This is a at 0 1 amplitude, minus 1 minus 2 minus 3 minus 4 like this up to minus infinity. Okay, this is about the step signal. It's a r of t is a some mt where t greater than or equals to 0, 0 for t less than 0. The representation is like this: t 0 amplitude at with slope of m. With the slope of m, the signal is r of t. So this is about the continuous. This is about the continuous. And coming to the discrete, r of n is equals to mn where n greater than or equals to 0 and 0 where n less than 0. So this is a signal. When it comes to the graphical representation, you will have this is R of n, and this is at 0, 1, 2, 3, 4, so and so. At 0 equals to 0, let us take this m is equals to 1 now. There is a slope. Slope is 1. That means at this point you will have like this, so and so. It should look like a linearly increasing curve. So this is a linearly increasing curve, and this is also linearly increasing curve, ramp signal. Okay, this is about the ramp signal. Coming to the parabolic signal. Parabolic signal, you can represent it by the P of t. Parabolic signal, which is represented by the P of t, and defined by P of t is equals to where t square by 2, t greater than or sorry, where t less than or equals to 0, 0 when t less than 0. When t less than 0. So this is about the parabolic signal, and signal is look like this. When it is t, this is P of t. Okay. Now comes to the discrete domain. So how it could be look like in discrete domain? P of n. This is a discrete domain. Then P of n is equals to where n square by 2, where n greater than or equals to 0, where 0 n less than 0. This is a discrete time signal, that is a parabolic. And in representation in discrete domain, look at here. At 0, we will have to substitute the 0, and you will get a signal like this. And first went 0, 1, 2, 3, 4, like this. So your signal is parabola signal. Next one, rectangular or gate signal. So gate means it just look like, for suppose in a door, in our doormat, you can see in our room, the gate is like this. It's like a gate. So that's why we are calling it as a gate function. See, the gate function, you can call it as a x of t, where x of t is equals to, the representation is a rect, R-E-C-T, rect of small t by capital T. So this is a mathematical representation of the signal gate function, or you can call it as a rectangular function. So how it could be look like in a graphical way? See, simply as I mentioned, it is a gate at 0, and it look like gate. So this is a gate, and this value is t by 2 and minus t by 2, t by 2 and minus 2. Where what is the t here? T is a fundamental time period. T is a fundamental time period, and its name it as x of t. It's a gate function. Okay. So this is the about gate function. Now what is the amplitude of here? Amplitude is A. Amplitude is A. So whenever you will have this is the standard representation of the gate signal, or you can call it as a rectangular function. Whenever you will see the rectangular function, the rectangular function must be this notation. T by 2 is a half of the fundamental time period, minus t by 2 the half of the remaining half of the fundamental time period, and you should remember it. It is a is a magnitude, or you can call it as a amplitude. So how you are going to represent this one? Like similarly, we will have the amplitude is A is in this case in between the minus t by 2 to where t is minus t by t to t by 2, you will have the amplitude is A. This is the first case. And what about the remaining case? And from the t by t to infinity and minus t by 2 to infinity, amplitude is 0. I am putting it is remaining place, that means else. So this is a mathematical representation of the rectangular function, or you can call it as a gate function. Okay. So next you can also, this one is not signal, it is a signum function. Just a second. After rectangular, it is a It is a signum function. This signum function, it is a, you can represent it as a u of, you can call some x of t, or you can represent it as a signum, SGNT, signum of t. So mathematically, signum of t is, you will have the plus 1 and minus 1, these two values only. Plus 1 is for the t greater than 0 and minus 1 for the t less than 0. Signum function, or you can call it SGN of t, is plus 1 for the t greater than 0 and minus 1 for the t less than 0. So these are the two cases. And if you look at the signum function graphically, see, this is SGN of t, signum function. This is 0 and minus infinity and infinity time period. So from the 0 to infinity, you will have the amplitude is 1 plus 1, and from the 0 to minus infinity, you will have the amplitude is minus 1. Okay, so this is about the signum function. But if you look at to the graph, if you observe clearly, this one is known function, it is u of t. This is a known function, it is a u of t. If you look at this one is u of minus t and flipped one, that means minus 1. You can take, this is a u of minus t. And if you multiply it by minus 1 means the signal will be flipped over there and it will be come across this point, it is u of minus t, minus into u of minus t. This is a second one. So if you look into the x of t or signum of t can be represented as u of t minus u of minus t. You can represent like this. One more thing, if you see, so this is u of minus t, this is a u of t. So if I combine these two, then let us take it as some x of t, not x of t. What is the value of u of t plus u of minus t, which stands from total 1 for the minus infinity to infinity. You can take it as a 1. You can take it as a 1. So that from here I am writing u of t value, first one. U of t is equals to 1 minus u of minus t. Then substitute over here, u of t is 1 minus u of minus t minus u of minus t, which is nothing but 1 minus 2 into u of t. This is a one representation. That means you can write SGN of t is equals to 1 minus 2 into u of minus t. This is the first one. Or else I can write u from here, from this equation, u of minus t is equals to 1 minus u of t. So same, I am substituting the signal over here. Then from this equation I can write u of t value is 1 minus, sorry, u of minus t I am writing, right? So from u of minus t I am writing u of t, first one is u of t minus of this u of minus t. U of minus t means 1 minus u of t. So that implies this is u of t minus into minus, you can write it as u of t minus 1 plus u of t, then you can write 2 into u of t minus 1. So same signal, signum of t you can represent as 2 into u of t minus 1. These are the two representations for the signum function. Next it is exponential function. Exponential means it is x of t is equals to e power minus at is a one exponential function. Same, x of t is equals to e power at. This is another exponential function. So how this signal look like? Exponential function, same two signals. One is the same. Let us take x1 and x2. So this is a x2 of t. No, okay. x1 and x2. So this is a x1 of t and this is a x2 of t. So this is exponentially, since it is minus is there, exponentially decreasing curve it is. That means it will start at the minus infinity amplitude and it will reach us at 1 at 0 and it reaches 0 at infinity. Not at here at minus at infinity you will get the 0. Similarly for this one, Let I put the t equals to 0, e power 0 means it is a 1. So 0 is here 1. If I substitute the t value, it is infinity. E power infinity is infinity. So that means at t infinity, I will get the amplitude is infinity. And coming to at e power minus infinity, I will get the 0. E power minus infinity, e power infinity. This is e power 0. Similarly, e power infinity, 0, e power next e power minus infinity. If you evaluate these all values, you will get the e power minus infinity 0, e power infinity is infinity, and e power 0 is 1. Here same. These are the two exponential signals. These all in continuous domain. If you look at the discrete domain, you can call it as a x of n is equals to a power n, and x of n is equals to a power minus n. These are the two signals, same. A power 0 is 1, this is a n, a power 0 is 1, so that this is a exponentially raising signal. That means you will get the discrete values. E power minus n means exponentially decreasing curve it is. That means the signal is like this. This is a 1 amplitude, and your signal is look like this one. Like at infinity, you will get the amplitude is, this one is 0. At 0, amplitude is 1, it's specific, and this is also 1 is specific. So these are the exponential signals in continuous domain and exponential signals in discrete domain. Next, sinusoidal signals. Sinusoidal signals are two types. One is sine signal, sine omega naught t plus phi, and another one is cos omega t plus phi. So these are the two signals. For pi, I am taking for the phi equals to 0. I am writing the graph. Just look at here. Amplitude is, let us take 1. In between 1 only you will get the signal. Just draw the dotted lines, and your sine signal varies from the, it starts from the 0, and your signal varies like this up to infinity. When it comes to the cos signal, combining the sine and cos, both the signals, we are calling it as a sinusoidal signals. This is x1 of t, that will name it, and this one is x1 of t, and this is x2 of t. I am writing it as a x2 of t. I named it, and similarly that is same. We will get the in between the plus 1 to minus 1. But now the cos, since it is a cos signal, will start from the minus 1. At 0, it starts from the minus 1 to, and like this. This is a cos signal. And look at here, I just consider phi equals to 0 for both the signals. Let us take it as a phi equals to 90 degrees, phi by 2. And the same signal at the same location, the same signal will start from the minus 90. 90 degrees means at 1. So at this position onwards, signal will start. That means not from the 0th location. Now it is starts from this point. And similarly here also start from the second one, and the signal will start from this point. This is pi equals to pi by 2. That means this pi, where it is in between this gap, and compared to this one, this is a pi by 2, and compared to this one, in between these two, pi by 2. So with respect to this signal, pi by 2 phase difference is pi by 2. For this two signal also, phase difference is pi by 2. This is about the sinusoidal signals. Coming to the next one, sync and sampling signal. Sync means sine t, sorry, sync means you can write it as a sync, S-I-N-C. Generally, sync means a sine cardinal signal. Sine cardinal signal. By combining this sine and C, we are calling it as a sync signal. So, sync T is equals to sine T by T. So, this is a representation. You can call it as a, you can write sine sync T mathematically. Value is 1 where T equals to 0. Sine T by T, sine T by T where T not equals to 0. And the area under this one, minus infinity to infinity, area under the sync function, SINC, sync T, dt is equals to pi by 2. Area under sync function is pi by 2. So, sorry, not pi by 2, it is pi. Area under sync function, it is pi. So, here this is a non-normalized function. If it is normalized, you can represent it as a sync pi t. It is a normalized one. Sync pi t, same amplitude is 1 for t is equals to 1. Then sine pi t by pi t for t not equals to 0. This is called, and over here minus infinity to infinity, and area under the sync normalized one, sync pi t dt is equals to 1. So, this is a normalized function. Okay, these are the two functions. You can represent it as a sync function without normalization, sync function with normalization function. So, the same function, whatever it may be, it is a sync function with normalized, or call it as also sampling function. Sampling function, and it can be represented as SA of t. SA of t means sync pi t. SA of means sync pi t. Okay. Now, in graphically, we can represent it like t. I am representing it is a sync t, and the next second one is a sampling of t. Sampling means it is a normalized one. See, look at here. This sync function look like this one. At amplitude t, at t equals to 0, amplitude is 1 for both cases. At t equals to 0, you will have the amplitude is 1 for both the cases. This is the sync function. Then coming to the, it's a compressed one, you can call it as a normalized by pi. Means the amplitude is same, but it's going to be, time duration is going to be decreases. The same signals are look like same only. You can call it as a sampling of t, sampling function. Okay. So, this is about the signal, or which are sync and sampling signals. So, what we have discussed, one is impulse signal and unit function, unit step function. Next one it is ramp function. Next parabola. And coming to the sinusoidal. Next one exponential. And what we study next, finally, it is a sync or sampling. So, these are the signals, basic signals we have studied, and the next topic we will discuss about the operations on basic signals. We are going to be study the operations on the basic signals. Thank you.